Every single one of us does every single day, but probably don't take the time to truly understand. We're completely decoding the architectural blueprint of sleep. We'll be looking at the hidden mechanics, the crazy chemical pathways, and those incredible brain waves that completely dominate our nights. Get ready, because you're about to see your nightly rest in a whole new light.
Okay, so let's just dive right in. Have you ever actually stopped to think about how incredibly bizarre sleep is? I mean, from an evolutionary standpoint, lying there totally paralyzed and completely unaware of your surroundings for 8 hours a day, that sounds like a terrible, dangerous idea, right? So why on earth do we do it? Why does our biology literally demand that we spend a full third of our lives completely unconscious? Well, that is the exact mystery we are unpacking today. Here is our roadmap for this explainer. 1. The mystery of sleep. 2. The sleep cycles explained. 3. Regulating the master clock. 4. Why sleep is essential. 5. When sleep goes wrong. And finally, number 6, a quick summary and conclusion. Let's get to it. Starting right off with Section 1, the mystery of sleep, let's set our biological baselines.
Clinically speaking, sleep is defined as unconsciousness from which a person can be aroused by sensory or other stimuli. That arousability part is absolutely crucial, because that is exactly what distinguishes being asleep from being in a coma. Now, historically, scientists actually thought our brains just kind of got fatigued, like a car running out of gas, and that's why we drifted off. But modern physiology tells a totally different story. Sleep is an active inhibitory process. Through some wild experiments, like isolating specific parts of the brainstem, researchers found out that without your lower brain centers actively inhibiting other parts of the brain, your cerebral cortex would literally never go to sleep at all. Your brain is actually working really hard to actively put you under.
So once the brain flips that inhibitory switch, what happens next? Moving right into Section 2, the sleep cycles explained, let's decode this 90-minute staircase of our nightly rest.
It is absolutely beautiful how your brain shifts gears here. When you're awake and alert, your brain is firing off these high-frequency, low-voltage beta waves. As you start relaxing and close your eyes, they smooth out into alpha waves. But as you fall deeper and deeper into sleep, the waves become much slower, but with massive amplitude. We call these delta waves. It's this profound shift from the rapid, chaotic buzz of waking thought down to a slow, powerful, synchronized rhythm of deep rest.
Let's walk down this cyclical staircase together. When you first drift off, you hit step 1, which is light sleep, marked by a slight slowing down into theta waves. Then, in step 2, your brain throws out these rapid little bursts called sleep spindles and high-voltage K complexes. Steps 3 and 4 plunge you way down into deep, slow-wave sleep. That's where those massive delta waves completely take over, giving you that deeply restorative, dreamless sleep. But then, something wild happens. Your brain shifts gears into REM, or rapid eye movement sleep. REM is often called paradoxical sleep, and for good reason. Your brainwaves suddenly speed right back up, looking almost exactly like you're wide awake. Brain metabolism spikes and you experience these incredibly vivid dreams. Yet paradoxically, your spinal muscle control is exceedingly depressed. You are essentially paralyzed, which, is definitely a good thing, so you aren't physically acting out those dreams of flying.
Now, for a typical night in a healthy young adult, the distribution of that rest is pretty heavily skewed. The deep, highly restorative, non-REM phases take up the bulk of it, about 75% of your total sleep time. The intensely active, dreaming REM phases occupy the remaining 25%. And throughout an 8-hour night, you're constantly looping through these non-REM and REM cycles every 90 minutes or so, with those REM periods actually getting longer and more pronounced the closer you get to morning.
Which brings up a massive question. How does your body actually know when to trigger these wildly intricate states of consciousness? On to Section 3, regulating the master clock, where we peek inside your internal circuitry.
Deep inside your hypothalamus, there's this tiny little cluster of neurons called the suprachiasmatic nucleus, or the SCN. This is your biological master clock, and it's directly entrained by light and dark. It works exactly like this. Light signals travel straight from your retina along a special pathway right to the SCN. During the day, that light signal suppresses sleep. But as the sun goes down and darkness falls, the SCN signals your sympathetic nervous system to activate the pineal gland. That gland then starts synthesizing and secreting the hormone melatonin. Melatonin basically acts as a timing signal, sweeping through your body to coordinate the onset of sleep.
So every single day, there is a literal chemical tug-of-war happening inside your head. On one side, holding the rope, is the wakefulness team, orexin, histamine, and norepinephrine. Orexin, sometimes called hypocretin, is incredibly important for keeping you aroused. Those neurons are firing rapidly all day while you're awake. But on the other side, you've got the sleep team, melatonin, GABA, and serotonin. Serotonin, which comes from the Raphi nuclei in your brainstem, heavily promotes sleep, while GABA actively dampens down brain activity. So falling asleep isn't just the wakefulness team getting tired and giving up, it's the sleep team actively pulling harder and winning that chemical tug of war.
All right, we know how it happens, but let's talk about the so what. Why do we go through all this trouble? Section 4. Why sleep is essential.
Listen, sleep is definitely not a luxury. It is a vital, non-negotiable biological need. While we're out cold, our bodies are running essential maintenance. Sleep facilitates neural maturation and cognition. It's essentially a memory triage system, consolidating whatever you learn during the day so it actually sticks. It also clears out the metabolic waste products that active neurons leave behind. It's literally taking out the brain's daily trash. And to put into perspective just how crucial this is, in laboratory studies, rats subjected to total sleep deprivation lose complete metabolic balance and actually die within 2 to 3 weeks. Without this nightly restoration, our entire central nervous system just begins to heavily malfunction.
On top of that, sleep plays a massive role in conserving energy. While you sleep, your basal metabolic rate drops by a solid 10 to 15%. This drop happens mostly because your skeletal muscles lose their tone and your central nervous system activity goes way down. By forcing us to totally power down and recharge our internal batteries, our bodies conserve all that vital metabolic energy we are absolutely going to need for the physical and mental challenges of the next day.
But what happens when this finely tuned architecture doesn't work perfectly? Section 5. When sleep goes wrong, let's look at system disruptions.
Let's compare two major but entirely different sleep disorders to see how this system breaks down. First up is obstructive sleep apnea. This is essentially a mechanical breakdown. When you sleep, your muscle tone naturally relaxes, right? Well, in sleep apnea, the muscles of the pharynx relax a little too much and the upper airway physically collapses. Breathing completely stops, your oxygen drops, and carbon dioxide builds up in your blood. That CO2 spike acts like a chemical alarm bell, jolting the brain awake just enough to gasp for air. And this can fragment your sleep hundreds of times a night. On the flip side, we have narcolepsy. This is a chemical breakdown. Remember orexin, our main wakefulness chemical? Well, narcolepsy is caused by the loss of those exact orexin-producing neurons. Without that wakefulness switch holding the line, patients suffer from overwhelming daytime drowsiness, sudden sleep attacks, and sometimes even cataplexy, which is a sudden, paralyzing loss of muscle tone while they are wide awake.
All right, let's bring all of these microscopic and macroscopic concepts together. Moving into Section 6, Summary and Conclusion. To quickly recap everything we've covered in this explainer, the entire architecture of your sleep is dictated by the suprachiasmatic nucleus, your internal master clock, which takes its cues from the light and dark around you. Under its direction, your brain gracefully steps down into the deep, slow-wave restoration of non-REM sleep before surging into the highly active, paralyzed state of REM sleep about every 90 minutes. This whole beautifully complex cycle is driven by a delicate tug-of-war between wakefulness chemicals like orexin and sleep promoters like GABA and serotonin. And ultimately, it is an absolute biological necessity, keeping you alive by restoring metabolic balance, clearing out brain waste, and cementing your memories.
I really hope this explainer has given you a newfound appreciation for the totally incredible unseen work your body is doing while you're resting. If you had fun unpacking this physiological mystery with me today, definitely make sure to subscribe for more explainers. I will leave you with this one final thought. When you turn out the lights and close your eyes tonight, your body might be shutting down, but your brain, it is just getting to work. So what memories from today will your active brain be permanently wiring together tonight? Sleep well, and I will see you in the next one.
Think about how incredibly bizarre sleep is.